and then I will go over to some realistic application, which basically we have done in the very recent past, and I will conclude. So let us look at this quotation, which is, given by one of the statisticians. And when I came across this quotation, I was really shocked, because it says, remember that all the models are incorrect. The practical question is how wrong they have to be not to be used. But when I really came out of my, state of shock, I realized that what is meant here is definitely true in the context of nuclear mean field models. We all agree that in most of the nuclear models, we make a lot of approximations. I don't think I have to list them. So in some way or the other, they are definitely not correct. So basically, quotation tells us that we should really look into it more deeper and find out that, if it's really viable to use such kind of model. Now, next slide is basically something more serious. This is basically I have taken a couple of lines from the column of the editorial published in Physical Review A 2011. And the title suggests that uncertainty estimates. This basically tells that most often the numerical calculations are presented without giving any estimate of the errors. Now, most of time, what is said that they are not very easy to estimate. So the editors are saying, is it a justifiable reason to get away with this kind of analysis? And moreover, they also say that when we publish a paper from the experiment, we cannot accept without having the error analysis done. So why the theory should be exempted from some such kind of analysis? So that's what I was saying, that it is not a motivation. It looks like that we need to really learn this kind of technique, and in fact, if you look at the recent papers, they are already appearing with all kind of error estimates. Now, and these error estimates become in fact more important according to this editorial if we really extrapolate our model, or if we make a prediction, or if we use for some unknown domain. So like yesterday we heard about this double beta decay and all those things, and so it looks to be that it's very important if we do those kind of analysis with our mean field model which were not fitted to those data, we must really think about putting some errors. So the types of error are basically the systematic error and the statistical error. The statistical error is basically, we can quantify it for most of the model, and in fact there is a systematic way, like what I call it a covariance analysis. It exists for getting such kind of error, and of course this is nothing new. This has been applied in the other area of the physics. We are not doing it. But as far as the systematic error is concerned, they basically arise because of something missing in our model or because of some wrong assumption, and there is no systematic manner we can deal with the systematic errors. Because if I want to get some systematic error, idea about systematic error, I need to have an exact model, and we don't have in most of the cases. Now, just to give you a couple of examples, what you see here is the model for the odd-even staggering. So, like just to demonstrate you the systematic error, so you start with some expression and use this expression to construct the data, what we call pseudo data. And assume that this is the data which is from experiment. So in this case, the exact theory is known, and then you consider the model which are approximate. So here I have taken two models, model A and model B. Model A has the parameter P1 and model B has the parameter P1 and P2, and it is basically P2 times minus 1 is for I. So where I is odd or even, that basically gives rise to the staggering. So if you do a fit, which we normally do it by using the chi-square function, you can really convince yourself in this case without really going to the chi-square minimization. Intuitively you can guess that for the model A, the P1 will be 0 because the pseudo data lies between plus delta to minus delta. So to minimize the error, I have to take P1 equal to 0. And for the case of model B, the P1 will be 0 and P2 will be delta. And I must mention in the exact model, like which is used to get the pseudo data in a quantity epsilon I, that is basically a kind of white noise which has the mean value 0 and the variance is basically you can calculate by using the standard definition of the variance. Now we can look into the residual error. By residual error I mean the difference between the experiment, or in our case pseudo data, and the calculated value. So you can see for the model A, the residual error basically fluctuates between plus delta to minus delta. So even by looking at the pattern of the residual interaction error, you can really feel that there is some sort of systematic error. Whereas in the case of model B, you see that the error seems to be like a random, which is more statistical in nature. And in this case, since we know the exact model, if you calculate the systematic error, like delta or sys, this comes out to be delta, and the statistical error is something times delta divided by square root of nd, which is a standard result that the statistical error goes down as we increase the number of data, of course 1 by square root times. If you look at the model B, you have the systematic error 0 and you have only the statistical error. Now let us look at another example which is I think more close to us. What I did is I used some simple form for the liquid drop model binding energy only with the 4 term, volume, surface, symmetry and Coulomb, and I generated the binding energy for about 850 nuclei, and again I call it as a pseudo data. So in a way exact theory is known, and I just modify little bit by hand the volume term. That exponent I made a to the power 0.999, and then I refitted the pseudo data. So my idea was that the various coefficient will get little bit adjusted and I will not have much error. I just want to see that how much approximation I should use in my theory so that it gets reflected in the residual error. So even when I took 0.999, you can see the error as you go up in A, it keeps on spreading. So again you can see from the residual error there is some sort of systematic. And when I made exponent 0.99, which is again close to 0.1, then you can see the error grows much rapidly. So definitely, I mean, of course there is no very clear-cut prescription to evaluate the systematic error until unless you have the exact theory. But at least if you look at the residual error, you can get some idea that the errors are not really statistical in nature. Now, for the rest of my talk, I will not talk about the systematic error. I will focus on the statistical error. So, idealistically, what we basically want is that you have the chi-square function. I am sure we are all familiar with this. Here, OEXP is nothing but any observable which is obtained experimentally. Then you have the corresponding theoretical value. P, bold P here means it's a set of parameters. And then you have the adapted error. And this adapted error basically have 3 components: experimental, numerical and theoretical. By numerical I mean that sometimes we make, that some numerical approximation we make. For example, if I want to solve my Hartley-Fock equation, I will do some basis expansion. And normally we don't take very large basis, so you definitely introduce some numerical error in our calculation. And theoretical error, for example, I mean center of mass. Normally we don't take any two-body operator to calculate center of mass. We just take some closed formula, and those formula are known to make some sort of more error in the light mass region. So basically, if you are trying to fit binding energy for oxygen, then basically you take large adapted error, so that your parameter do not go into the crazy region. Now, since we have the objective function, we can always construct the distribution of the parameters, I mean also known as the maximum likelihood function, which is maximum when the chi-square is minimum. And since we have the distribution for the parameter, I can always calculate the average value of any quantity A. I am just saying quantity A because this A could be parameter, it could be observable. So we have the objective function, we have probability distribution, we have this expression for getting the average value. So far no approximation. And I can always use the Metropolis algorithm to sample the parameters in such a way that they carry the information about my probability distribution function. And once I have that, I can just write my integration in terms of the summation, so I have the average. I can also calculate the variance, which is nothing but the deviation from the average value. So once I have this, I can get the error of the quantity A. I can also calculate covariance. That means the delta A times delta B, an average of this quantity. Likewise, I can calculate the Pearson correlation coefficient, because what we mean by information content of a model, that we want to really study the correlation between the various parameters of the model, observables,